So welcome to the Machine Translation Day of the CLSP Summer School. I'm very pleased to say that we have two wonderful, wonderful speakers. So not only are they experts in machine translation, but they both give really amazing talks. So I'm hoping that we're in for a really good time. So first up, we have Adam Lopez, who graduated from the University of Maryland College Park not too long ago, and who's now a postdoc at the University of Edinburgh. So he's going to give us the introduction to machine translation, and then for the second lecture, John De Niro will give us introduction to word length. Adam.
Okay, so hopefully I'll manage to live up to any absurdly high expectations that Chris set for all of you, but I'm not making any promises. So, I'm going to talk about modeling machine translation, how do we do search over models, and how we evaluate it. And I'm going to sort of open the talk by giving you sort of a brief introduction to the application area. Since we're not really talking about sort of more theoretical areas like machine learning, we're talking about more of applied field, and I'll try to relate that back to some of the stuff that you saw earlier this week. So here's the problem that we're trying to solve, right? This is a real problem. Basically, the problem is, given some information in this kind of form, you want to be able to understand this information. So looking around, I'm guessing there are probably some people in this room who understand what's written up there on the screen. I don't know if does anyone? Okay, so I figured there would be at least a couple of people, but most people in this room probably don't understand what's written up there on the screen. And so the problem that we want to solve is to take this information that's encoded in this text and turn it into some information that we actually can understand. So hopefully this is something that everyone in the room will understand, and occasionally I do have Chinese speakers come up to me after this talk and say that, this is a fairly non-literal translation. I'll talk about that more in a minute, but don't start out raising your hand and giving me too many objections at the outset. So this is basically what we want to solve. We want to take this Chinese sentence and turn this into an English sentence that we understand. So obviously this is a fairly old problem, right? So people have been writing about this problem for quite a long time. Here's a painting from several hundred years ago, which is based on a story that's in a book that's even much, much older, basically, which is about this problem. So we have all these people that are trying to build this tower, and it turns out that they need to understand each other, and they're communicating in two forms which are not mutually unintelligible. In terms of automation, this problem is also still quite old. So here's probably one of the first mechanical devices which tried to solve this problem. It's called a mechanical brain. It was developed in France by an inventor in the early 30s. And basically what this device did, it could store multiple dictionaries and allow you to input words in one language, coded in one language, and output words coded in another language. Okay, so this is quite an old problem. In fact, this invention is quite a bit older than computers themselves. So here's one of the earliest computers, the ENIAC, which came online in 1946. And just to put that number in perspective, the first sort of suggestion that we use computers to try to solve this problem of translation happened not too much later than the development of that machine in a letter which was written by Warren Weaver and circulated amongst a number of eminent scientists in 1949. How many people in the room know who Warren Weaver is? Okay, so probably all the machine translation people know who Warren Weaver is. So I'll come back to that in a little bit. And so the point I want to make about this is that there's been an enormous amount of research in this area, basically continuously since 1949. And so here are all these decoders that have been developed to solve this problem. Right? So we were talking about these coders, and so a lot of people have now gone forth and tried to build decoders to solve this translation problem. This is just a small sampling of, and they have all these names. And occasionally, if you're doing research in this area, you'll come across these names. And so it's just The purpose of doing this is just to, of me telling you this, is just to sort of set the context here. This is a very, very hard problem, right? And it's unlikely that we're going to solve it in the next 5 years, but we should keep trying, right? So there's also been a lot of different sort of approaches to try to solve this problem, and they go under sort of various names. The one that I'm actually going to talk about in this talk more or less exclusively is this statistical NT. And so this basically is going to be in line with the lectures that you've seen in the last couple of days on statistical methods for natural language processing and machine learning. But the point of this is just to say that there are a lot of other approaches out here because this is a very, very, very hard problem. OK, so perhaps it's useful to actually try to illustrate why this is a hard problem. So let's take this example sentence that we saw earlier. So how many people in the room have actually learned a foreign language at some point or know multiple languages? So most people know multiple languages. So an exercise that you might have done while you were learning a second language is to get a parallel sentence pair, or at least pairs, groups of words in one language and the other, and try to draw correspondences between them. So that's going to be quite difficult for most people in this room because you can't read Chinese. So I'll help you out a little bit by giving you the gloss for the Chinese sentence. So this is sort of roughly what each of those Chinese words up there corresponds to, right? And so now what you can do is you can actually try to do this exercise. So for instance, the first Chinese word there is going to correspond to the first English word. And so now let's look at the second Chinese word. That actually corresponds to a word that's way across towards the end of the sentence, right? And we can go ahead and fill in all the rest of these correspondences. So this is one sentence, but this sort of illustrates a lot of the problems in a very sort of general way that you're going to encounter when you're trying to solve this translation problem. So one thing I want to point out here very quickly is that this sort of activity of taking these parallel sentences and drawing these correspondences between them is called an alignment. And so basically what we've done is we've aligned the words of each sentence, hopefully the smallest units of meanings that we can find, not necessarily. I think in English and Chinese is a fairly reasonable thing to do. For more morphologically complex languages like German, this might be even a more difficult activity. But even for Chinese, it's actually somewhat difficult. Right, so you'll notice a few things that are going on here. So we have some fairly strong non-literal translations. It turns out actually that you will actually frequently see this Chinese word being translated as this English word, but this is sort of fairly non-literal, right? In fact, one thing that's going on here is we've got a verb that's been turned into an adjective. And so there are lots of these kind of difficult sort of non-exact things going on. Another thing that you'll probably notice is that we have two English words that are aligned to the same Chinese word, right? And so this one-to-one correspondence between words, that's sort of a nice idea about how we might do translation, is not exactly precise. And part of the reason for this in this case is that the English word requires a determiner, while the Chinese doesn't really have any such notion of these determiners. But when we are generating an English sentence, we want to be able to handle this determiner. And so there's sort of a corollary to that. So that you could have an English word that's aligned to multiple Chinese words. And again, in this case, it's actually arguable whether or not this word very should even be aligned to that word clear. So this is some modifier that appears in the Chinese, it doesn't appear in the English. And in most of the English translations of the sentence, that word just sort of vanishes. So perhaps it's reasonable to align that word to clear. And so this is another thing that I want to point out is that if you have humans performing this activity of aligning these sentences, they don't always necessarily agree on how to do this. So this sort of captures a lot of our intuitions, but it's fairly imprecise. So one last thing is we could have words, for instance, in the English, we have some syntactic material, essentially, that is completely absent from the Chinese sentence. Right? So we've constructed this English sentence in such a way that these words just simply don't have any way of corresponding to the English sentence. And so the people in the room who are more linguistically oriented are probably not going to be terribly happy with the sort of shallowness of this analysis. There's actually a whole lot of linguistic phenomenon that are going on here that sort of explain what these things are doing. But this is just something you can see at the surface level just by sort of inspecting these sentences. And part of the reason for me to sort of describe this at this sort of very superficial level is because most of the approaches that I'm going to use to try to solve this problem are probably relatively superficial. They work, so that's actually okay. So one last thing, actually a couple more things I want to point out. So obviously, this is one possible translation of this Chinese sentence. You could have different translations, and this sentence also perfectly conveys the meaning of that Chinese sentence, right? In fact, it's typical when we're developing these systems to obtain a large number of translations. So in fact, all of these sentences here are sort of reasonable translations of this Chinese sentence, and they largely preserve meaning. And so one other thing I want to point out about this is that there's a lot of variation at the sentence level. There's also a lot of variation at the word level. So, for example, we've got this one Chinese word that's translated as however here, but it's actually translated 4 different ways in each of these sentences. So one thing that sort of comes out of this is that your translation model, your translation system may have many, many, many different ways of translating a single word, and certainly it's going to have a lot of different ways of translating a single sentence. And so in some sense, this is going to be somewhat of an ill-posed problem, right? This is sort of a difficult problem to solve. I can't necessarily say, this is only the truth, or that's only the truth, or that's only the truth, or something else that's not on this screen altogether. So I told you I was going to talk about statistical machine translation. There's sort of a practical reason for this. This is what a lot of people in the field are doing research in today. And so in fact, if you've used Google Translate, you may be aware already that statistical techniques are basically what underlie this Google Translate system. And so what's nice about these statistical techniques, and you've sort of seen some, for instance, in Jason's and Mark's lecture, is that they are somewhat language independent. Now they actually the techniques are going to show you actually make a lot of sort of assumptions about things that are going on in language that aren't necessarily true. But it turns out to some sort of reasonable degree, we can think of them as being language independent. I'm not going to make a very strong claim on that point because I think it's a little less true than a lot of people like to think it is. But this is basically, an important area of endeavor. Google Translate currently translates between 41 and 41 languages. So that's actually quite a large number of language pairs. And this system just came online within about a little over 3 years ago. And so to be able to ramp up to that number of language pairs suggests that actually there is some merit in these statistical techniques, even if they don't always get exactly the right answer. But you can actually use it to translate Arabic news quite accurately. Chinese is a little less good. Some other languages are a little less good. Some are good, some are not so good. So let me just sort of define statistical machine translation for you, because you'll see sort of a lot of different definitions in the literature. Here's basically what we're going to do in a nutshell. So we're going to develop a model of translation, which I'll sort of give you a feel for what that means, a model of translation that can be learned from data and used to predict the correct English translation for new Chinese sentences. So if you've been in the lectures for the last couple days, most of these words should start to look familiar to you, right? So we have some model that we're going to use to make predictions, and we're going to learn that model from some amount of data. So one thing that's different here, so for instance, if you saw the machine learning lectures on Tuesday, is so a lot of it was talked about there. You might have seen there was a discussion. There are various types of prediction problems we can do. We can do classification, we can do regression, and then there was this little bullet at the bottom of the slide that said structured prediction, which said, well, structured prediction is an example of a type of prediction you might do. We're not going to talk about it. So this talk is all about structured prediction. And basically what this means is our model has to predict some extremely complicated output. And so you just saw an example of what that extremely complicated output looks like, right? So we're given a Chinese sentence, And our model has to predict, out of all possible English sentences that might exist in the world, the right English translation of that Chinese sentence. So that's a quite hard problem. There's basically an exponential number of outputs. And so that's essentially, among other things, what makes it difficult. But basically, we have, so we're going to develop a model that does this, right? We're going to develop a model that when it sees a new Chinese input sentence, it is going to predict what an actual human English translator might output as a translation of that sentence. The prediction may not be actually correct, but as we saw, again, it's somewhat of an ill-posed problem because there may be many correct English output sentences. And so basically, what my talk is going to be about is these two elements of this problem. There's another sort of important bit, which is that you have to start out with some data from which you learn your model. And so that's basically what John's talk is going to be about. And this is a really incredibly hard problem. So these other problems are really, really hard, and this one is even harder. And so there's one sort of last bit of information that I want to sort of briefly talk about for maybe 5 minutes, and that's data. So we actually need to have some data in order to learn these models. We're not going to write them down by hand. It turns out that they are much, much, much too big and much too hairy to figure out how to do this. And so, since we're sort of casting this in a machine learning setting, we're basically going to need some data from which we can learn how to do this. And so it probably will not surprise you to see this image in a talk about machine translation. So when you start to do research in MT, you're basically required to show this image in many talks. It's in the contract that they make you sign when they give you the free toaster. So basically, what is going on here? So this image this object is the Rosetta Stone. It was discovered a few hundred years ago, and it turns out that this object has text in 3 different languages on it. I think it was Demotic, Greek, and hieroglyphics. Someone in the room will surely correct me. But the point is that at the time that this object was discovered, the actual meaning of the hieroglyphic scripts had been lost, but the other 2 scripts were still understood. And so a very sharp Frenchman, Jean-Francois Champollion, basically using his knowledge of the other 2 scripts, figured out essentially what the hieroglyphic script meant. So what this is basically, this is called a parallel text, right? So I have some text that expresses meaning in multiple languages. And basically doing this, a human can actually learn how to translate a third unknown text. So but basically what we're going to do is this is what our machine learning system is going to do. So we need some parallel text. We're not going to use the Rosetta Stone, so we'll go and look for something that's published in multiple languages. So for instance, you might try something like this. Unfortunately, gathering text like this turns out to be problematic. They're copyrighted, although they are translated in many languages. You won't necessarily learn how to translate the Financial Times by training a model on this document. We can look for other documents. So there are other books that are in the public domain. So for instance, here's a book. I'm told it's a good book. This book is translated into more or less almost every language that you can think of. So that's good. It turns out that in terms of our machine learning algorithms, it's actually a relatively short book. And again, you still won't actually be able to translate the latest news from the Washington Post or the Financial Times or whatever. If you want more current data, actually there's a huge industry that's devoted to essentially producing training data for machine translation systems, and they give it to us for free, which is quite nice. So for instance, this organization publishes documents in many, many, many languages. It turns out this is not the only sort of governmental organization that does this. There are lots of other government and news organizations, for instance, in many bilingual countries, Canada, Hong Kong, the European Union. You print out both governments and news agencies actually develop a lot of material in multiple languages. And so essentially what you can do is you can go mine this stuff off the internet. Sometimes you might want to translate something other than sort of government legalese. So one last strategy is to actually go and mine information off the internet. So this is just a random page that I pulled up off the internet. How do you find stuff like this? Actually, it turns out that there are very simple structural cues. that you can use to find documents like this. So you can actually sort of write a very simple web crawler to go out and find parallel documents like this. There are other strategies. You can actually hire people to translate documents. I'm told there's a company in Thailand that's doing this. And there might be other sort of clever ways to get data. But actually, so this is not necessarily sort of the most interesting bit of what's going on here, but it actually is important. You need to collect a large amount of data in order for these models that we're going to learn to actually do anything useful for you. So this is sort of an important part of the problem. I just want to mention this. And this is sort of, because this is really an applied area, I think it's fair to give you some context about this. OK, so that's quite a long time I spent on that. Let's talk about modeling. So basically, this is what we're going to do. We're going to throw this into a probabilistic setting, right? What I want to do is, given a Chinese sentence, I want to have some model which tells me the probability of any English sentence given that Chinese sentence. Right? And so this model, among other things, is going to have to tell a story about how that Chinese sentence gets transformed into an English sentence. And in some way, that model is going to have to be learned for the data. So here's our gloss again. So when we're sort of developing these models, a good strategy to use is actually to come up with the dumbest possible model that you can think of that might solve the problem. Right? So what is the dumbest possible model that you can think of to translate this sentence if you've seen some training data? So one dumb way of doing this is to say, if I've seen this sentence before in my training data, I simply just output the corresponding sentence, the corresponding English sentence. So essentially, you know, the probability is going to be just, in most cases, it's simply going to be 1 for this English sentence and 0 for everything else. And so that actually seems like an incredibly dumb model, right? It's not totally dumb. Actually, there's human translators, when they actually sort of work in industry, often use a device called a translation memory, which basically says, you know, if I've seen some sentence before and I've already translated it, well, we'll just reuse that translation. And this actually is really common, especially if you are translating sort of government texts and news texts. And you know, politicians say the same thing over and over again, and so it's not really that unusual to think that you might be able to reuse the translation. So this is actually not an unreasonable thing to do. On the other hand, this model doesn't really work very well if we haven't seen this complete Chinese sentence before, right? So one way you can sort of think about this, you know, in the context of the machine learning talks we saw earlier, this is a model that has very, very high variance, right? So it basically fits directly to the training data, but it doesn't really generalize very well. So what we probably want, so if we thought about this problem for a second, we already thought about it a little bit, we probably want something that looks a little bit like this, right? We want some model that is going to be able to translate words. And so although we might not have seen this whole sentence in the training data, it's not unreasonable to think that we've seen most or probably all of these words in some large amount of training text, right? So we want some model that's going to be able to take those words and rearrange them in some way and perhaps generate some extra words and delete some Chinese words and generate a sentence, right? That's obviously sort of a non-trivial thing to do, but this is basically, this is essentially the problem that we want to solve, right? So here's a question. How are we going to define the probability of an English sentence given a Chinese sentence, assuming that we're able to come up with something like this? And so, as I said, the model is basically going to tell you a story. The model is going to tell you a story about how this Chinese sentence gets translated. And so what we need to come up with is a story that ends up looking something like this, right? But we have to define it somewhat formally. So here's how our story is going to work. Here's a model that's actually much more reasonable than the model I showed you. So we're going to translate based on words because we think that words sort of encode some important element of meaning. So each word, we're going to say, the first part of the story, each word is going to generate some number of copies of itself, right? So this word over here is going to generate one copy of itself. And basically what this copy is going to do is it's going to turn into a single English word. So because in general word-to-word correspondences tend to be one-to-one, most of these things will turn out to generate exactly one copy of itself. One thing about this is that, so we can actually parameterize this probabilistically by saying that we call this a fertility. So this word actually generates one copy of itself, and so we have a probability of the fertility of this word being 1. That's just a parameter in the model, right? This is just some number. It's a number between 0 and 1, and so it's an actual probability. And so you've seen enough probabilities now. Hopefully this makes sense to you. And so we're going to just have some parameter for every single word in this sentence. So most of them generally have a fertility of 1. But you do have, so for instance, you have one word that has a fertility of 2. So this, again, that's just a probability that that word actually generates 2 copies of itself. And you have a couple of words that have a fertility of 0, right? So these 2 words, but and very, they don't generate any correspondences in the Chinese sentence, right? So here, so you'll notice that this word has a fertility of 2, and these words have a fertility of 1. Okay, so that's nice. But we also want to be able to handle words that appear in an English sentence that actually don't have any corresponding word in the Chinese sentence. So, right, so we already have a way through this fertility parameter of modeling the fact that a Chinese word might not have a corresponding word in the English sentence, but we don't have any way of doing that for English. So what we're going to say is that there's some object which we call a null word, which shows up here. And this null word also has a fertility as well. This is parameterized slightly differently, but it's OK. Basically, this thing is going to generate 2 English words that sort of spuriously appear in our English sentence, right? So the next thing that's going to happen, so once each word has decided what its fertility is, and each of these fertility decisions is a probabilistic event and has a probability associated with it. OK? So once we've done that, we're now going to take each of those copies of the Chinese words, and we're just going to translate them. So they're going to translate into exactly one English word. So for instance, this Chinese word over here is going to translate into the word however, and there's a probability associated with that. OK, so there is a probability that this Chinese word translates into that English word. And this probability, again, this is some number between 0 and 1. It's probably going to be less than 1 because, as we already saw, this Chinese word can translate into many possible English words. So now we do this for all of these, all of the Chinese copies of the Chinese words get translated, again, just under some probability. Essentially, the probability just encodes, it's just a probability of the single Chinese word independent of anything else translating into that English word. It's even independent of what the other copy of the Chinese word translated to. So now what we have to do is we actually have to rearrange all these words, right? Because you can see that this is not really the correct order for our English sentence, and we've already seen that the sentences tend to be reordered. So we don't have a very good model for doing this, but one thing we do know is we do know how many words we have to move around, right? So essentially what we're going to do is we're just going to sort of slot each of these English words into some position on this grid. So what we're going to do is we're going to take the first word and we're going to put it into the first slot. How do we parameterize it? We're going to parameterize this using a very sort of dumb parameter, which we call distortion. And essentially what this means is sort of relative to its position in the unreordered sentence, where does it appear in the final output? And so by giving it a distortion of 0, it means I just sort of keep it where it is, right? So it doesn't change position at all. Relative to its current position, the distortion is 0. So this word north, it actually moves around quite a bit. And so what happens is the distortion of this word north is 8. Basically what that means is that it should have appeared here, but it appeared 1, 2, 3, 4, 5, 6, 7, 8 positions away from where it should have appeared. And so we just have a parameter that basically just says, what is the distance that this word moves? And there are actually some other things that are going on in sort of the actual implementation of a model like this. The parameterization is slightly different from what I'm showing you here, but this is the basic idea behind it. And so this sort of concept, so all these concepts that appear in this model, this fertility, word translation, and distortion are sort of very common concepts that tend to sort of crop up over and over and over again, the modeling this problem.
You have a question over here?
Yes?
Yeah. So how does distortion normalize for the length of the set?
Actually, that's a good question. So in the actual implementation of this particular model, we don't actually allow. First of all, we tend not to allow distortions greater than some fixed limit. But the other thing is that this distortion model is what's called deficient. And so what that means is this distortion model actually assigns probability to events which cannot occur. So it doesn't actually know anything about the length of the sentence. What it will do is it can actually say, I can assign probability to all the words appearing here, or I can assign probability to words appearing past the beginning or past the end of the sentence. And so the only sentence we'll actually consider are ones in which all the English words are in some position here. There is, generally in the parameterization of these things, the distortion is relative to wherever the last word was placed. So essentially, this distance has to do with, relative to the word in this output in this order here, how far are they apart in the final output. Does that make sense? So there are a whole bunch of bad things going on here. Thanks for asking that question. This is actually really a bad part of this model. But we need some way of sort of parameterizing this. And so now what we can do is we can fill in all of these slots. And then all we do is you just read off the English sentence, and we're done. Right? So what just happened here? Basically, we now have some story about how the Chinese sentence gets transformed into an English sentence. And because we've had essentially each arrow in this diagram has a probability associated with it, we can essentially define the probability of the English sentence and this particular alignment given that Chinese sentence. And that's just basically the product of all of those small probabilities that you saw earlier. Right? So I haven't written them out because it turns out to be quite a long equation. And there's some tricky things going on with the epsilons up there. But basically, here you have the probability of this whole thing, right? We have a probability of this whole event as a product of the probabilities of the independent events. So one thing I want to point out about this is that it would be nice if you could learn a model like this from data. Our data doesn't look like that. We didn't actually see all those events. Our data, when we're actually learning, looks like this. So you don't actually see any of the alignments in the data. That turns out to be, that's unfortunate that the human annotators that generated all this data for us forgot to put in the alignments. So basically that's what John's going to talk about later. But it does bring up one sort of important point, which is that in order to actually get the probability of the English sentence given the Chinese sentence, you essentially have to sum over all of the possible alignments that might have occurred between these two sentences. And so I'm not going to talk about this a great deal, but it's important to remember that the probability of the English sentence given the Chinese sentence actually depends on all possible ways that you could align them. So this actually turns out to be somewhat complicated. So this thing that I just showed you is called the IBM model. It's actually IBM model 4. And it's got these three probabilities associated with it, these fertility, word translation, distortion probabilities. So that seemed like kind of a screwy way of sort of describing how translation works. Like you wouldn't imagine that a human translator actually does something like that. Or maybe it's not totally unreasonable, right? So word translation probabilities actually sort of make a lot of sense. You can think of those word translation probabilities as essentially describing a probabilistic dictionary, right? And that's actually a reasonable thing to think about. So in some ways, this model is not totally unreasonable. It does capture something about our intuitions about the way translation works, but it does have some problems. So one thing that may or may not have been evident to you is that the complexity of that thing is exponential in sentence length. Essentially, the reason for this is because your Chinese sentence, the model allows you to sort of arbitrarily permute the words in the Chinese sentence. And so if you sort of arbitrarily permute some order, there's an exponential number of permutations, and so that's bad. As we sort of already discussed, this reordering model is pretty weak. The output is not very fluent. And so here's something that is perhaps somewhat important, is that you have to make a huge number of decisions in that model, right? A lot of things, what that means is that if any of those decisions, if I make the wrong decision at some point, a whole lot of things can go wrong. So let me just sort of show you what's going on. So let's suppose we want to look at the translation of these, the second through the fourth Chinese words there. What I want you to see is the number of decisions, the number of probabilistic decisions that have to be made in order for that thing to be translated into those 4 words. It's actually quite a lot of decisions, right? And so at any point, it's quite possible that the parameters of our model are not quite correct. And so if at any point we make a wrong decision, we're basically not going to get the right output. And again, the other thing to notice about these decisions, they're largely independent of each other. So this can be somewhat problematic. And this is unfortunate because actually you might expect that, and in fact it is the case, that those 3 Chinese words frequently correspond to these 4 English words. And so it's not totally unreasonable to think that you've seen these 2 sequences several times in correspondence with each other in the training data. And you would like for the probabilities of all these things happening not to be essentially independent of each other. Or you want to be able to model that in some clever way. So whereas the model that I showed you earlier, where I just take the sentence, I memorize it, and I output it again, that's a model with high variance. This is basically a model with high bias. This model might not actually be strong enough to model the problem that we're trying to solve here. So let's think of another way that we might do this. So I just sort of introduced the idea that you might have sequence of words that correspond to other sequences of words. So here's a different model for how we might solve this translation problem. We're going to take our Chinese sentence and we're going to break it up into groups of words. So here we've broken up this Chinese sentence into these groups of words. And basically, what we're going to do now is that each of these groups of words can translate as a single unit. And the output of this translation can also be multiple words. So we take this first word and we'll translate it. We can still do word-to-word translation here. So that's an important thing to point out, is this Chinese word can still, this is essentially the same probability as we had in the previous example that you saw. And so we're going to do this with all of the other sequences of words. So in sort of the NT literature, these things are called phrases. They don't necessarily have to be linguistic phrases in any sense that you think of. They're just sort of arbitrary sequences of words. One thing you'll notice here is that we don't need any sort of fertility or epsilons or anything like that. Essentially, these things don't have to be the same length, right? So this Chinese phrase here translates to an English phrase that's slightly longer, has more words in it. And so this thing is sort of able to sort of, by sort of eliding some of the details, is able to capture sort of word insertion and deletion in the context of particular phrases. And so the nice thing about this is that, if your model has parameters for translating this thing in this way, then basically you can just sort of translate that thing for free. You just make one decision. Basically, that decision is the probability of that English phrase given that Chinese phrase. The other thing you'll notice about this model is going to have a large number of parameters. So the last thing we have to do is we have to reorder these things. And basically, we can translate this English. We'll output this thing in order, but maybe we'll pick something from later down in the segmentation and throw it over here. And this is parameterized by something that looks very much like the distortion parameter that I showed you earlier. It basically has to do with the number of words that you jump over. Right? So the parameter is going to depend on the number of words that I jump over to insert that thing earlier than it appeared in the output. So then we're just going to reorder all these things. Again, each of these decisions here, each of these arrows corresponds to some probability. And so the probability of the English sentence and this alignment, given the Chinese sentence, is just going to be the probability of the segmentation, which in many of the models tends to be uniform, but you could actually assign some probability to it. The probability of these phrase-to-phrase translations and the probabilities of the rewordings, right? And so that's basically, this is the model. And so this is basically the Google model. This is called phrase-based translation. And so if you spend more than a couple of minutes looking through the recent statistical NP literature, you'll see this model usually cited somewhere on the first page of the paper, if not in the title. So this is sort of a useful model to know about. And again, this doesn't seem like totally realistic in terms of the way that human translators might translate, but it's not completely unreasonable, right? So you frequently do have sort of phrase books that give you whole phrases of translations, and so you can think of this phrase-based model in some ways as being sort of a probabilistic phrasebook. That's not a completely unreasonable thing to do. But it still does have some problems, right? So we think that maybe the whole problem where we had way too many independent decisions has gone down. So this model, essentially what it's done is where, the first model I showed you where we just take the sentence and memorize it, that was a model with high variance. And the word-based model that I showed you, the IBM model, is a model with high bias. This thing is somewhere in between. It's not really clear whether this is the sweet spot, but a lot of people are using it, so maybe it is. But you can still see there's sort of a lot of weird things going on here. We haven't really solved the complexity problem that I talked to you about earlier, right? And the reason for this is you essentially have an exponential number of segmentations, and you have an exponential number of reorderings. If you thought in sort of the degenerate case, you just did word-to-word translation, and you can arbitrarily permute those things, then you still end up with an exponential number of permutations. And that's bad. And again, we have a weak reordering model. The output tends to be more fluent than what you saw in the IBM models. So whereas the IBM models give you what people often call word salad, this will give you something called phrase salad. So you have these sort of chunks of fluent meaning, and then there's some strange point in the middle where the two words don't sort of make any sense, and then you have some more chunks that look okay. And so you tend to get something like this. This is something that we ought to be able to solve, right? So let's think about this for a second. So one thing I would again sort of point out very, very quickly is that the models that I just showed you, all of the models, you can think of this way. So we have some set of decisions that are made probabilistically, and we're just going to take the product of all those decisions, and that's going to be the probability of the English and the alignment given the Chinese. And again, to actually get just the probability of the English sentence given the Chinese, I have to sum over all those alignments. It turns out that that tends to be intractable. And so I'm going to just make the following approximation to what we actually want. So we're going to call this approximation p hat. And basically, we're not going to sum over the alignments. We're just going to take the best alignment of whatever came out of the decision process and say that's the probability of the English sentence given the Chinese. And so this is a very, very common approximation. This is a bad approximation, but for various reasons, doing it the right way tends to be intractable, and so we often do it this way. Now, a lot of smart people have been thinking about this in the last year or two, and actually are starting to come up with solutions so that we don't have to make this bad approximation. But for the most part, the models that you see will make this bad approximation. And so when we actually want to find the best English sentence given a Chinese sentence, we want to predict, all we have to do is we've got some probability over all possible English sentences, and we're just going to take the one that maximizes that probability. That's going to turn out to be somewhat non-trivial. Obviously, we have to have some way of enumerating all the probable English sentences, because we don't want to enumerate all of them. And so that is still going to turn out to be a nasty problem, which I'll talk about in a minute. But first, I want to talk about something that's broken in our model. So I sort of told you that we don't actually have any way we don't have a strong way of modeling these reordering decisions. In fact, if you looked very carefully at the models that I showed you, because almost all the decisions are made independently, it turns out that the optimal English derivation often tends to be that I just pick the most probable translation for each word or each phrase, and then I just pick the sort of I essentially can just sort of leave them in place, because it turns out that the optimal distortion tends to be 0. And so I don't actually have to do very much work to find I'll basically just end up lossing that whole Chinese sentence. And that won't tell me anything that's very interesting. What we actually want to do is we want to make sure that the probability that the translation of those Chinese words in English sort of depends on the translation of the other Chinese words. So we want to tie these things together in some way. One thing that we can do, so let's look at this for a second. So now we've got this probability of an English sentence given a Chinese sentence. So let's suppose along the x-axis here we have all the English sentences. Actually, this is just 1,000 English sentences. And the y-axis is just the probability associated with each of those sentences. And this is basically the model that we've come up with, right? It turns out there's sort of a different way of thinking about this thing. And this goes back to the Weaver paper, which I mentioned earlier. So I asked if people knew who Warren Weaver was, and only a few people raised their hands. You might have possibly heard of a book that Warren Weaver was a co-author on. It's called The Mathematical Theory of Communication. Okay. So hopefully people, even if you hadn't heard of Warren Weaver before, you have heard of this book. The first author, Claude Shannon, is somewhat important, developing information theory, basically a theory of communication. So Shannon was a smart guy. But basically, this book describes translation of a signal over some kind of channel in which it gets distorted, right? And so you can think of translation in this way. I have some signal, say an English signal, that I'm trying to transmit to you, and it goes through some process, a noisy channel, which distorts it and turns it into Chinese. And so your job is basically to decode that sentence. And so the principles that sort of Shannon laid out in here in the mathematical theory of communication can actually, essentially can be applied to sort of improve our models by thinking of them in this way. It actually goes back to the work by an 18th century Presbyterian minister who was also a mathematician, manuscript published in 1764, in which he lays out something called Bayes' theorem. So here's Bayes' theorem. So we can think of we can decompose the probability of the English sentence given the Chinese sentence in this way, right? So this is just a theorem. You can actually derive this from a couple of rules of probability, but this is basically what it is. And so, whereas before I was trying to sort of model that thing directly, now I'm going to step back and actually redo it this way. And so what does this tell us? So now what I'm going to do is I'm going to model actually the probability of the Chinese sentence given an English sentence. And I'm going to call that the translation model. And this turns out to be not too difficult, actually. I'll just model the probability of Chinese given English by reversing the models that I developed earlier. Okay? But then I'm also going to multiply that thing by this other thing called a language model. So this, in sort of Shannon's terminology, this basically is the original signal that you wanted to transmit, and this is the channel model. So you can think of it this way. I have some probabilistic model that generates English sentences, and then I have some probabilistic model that distorts those English sentences into Chinese. And so now the process of recovering the probability of recovering the English sentences basically is a probabilistic process where I sort of apply these two models in tandem. And so what's nice about this, well, I already sort of told you that model, if I model it directly, was broken. But if I do it with this and this, now essentially what I'm saying is, because this the translation model is kind of broken and it generates very, very bad English, I'm essentially correcting that by giving it some probability. This is almost like, this is like a prior and a Bayesian model. It basically says, I have some notion of what English sentences should look like, and so I want to bias my model to generate sentences that look like English. So now all I have to do is I have to come up with some way of essentially assigning probabilities to English sentences. So there's one last thing. Here's a normalization term, which we need to ensure that we're working with valid probabilities. For the applications I'm going to talk about, we can tend to ignore this thing, and so we end up with something like this. So now all I need to do is I need some probability of an English sentence, some way of assigning probabilities to English sentences. You already saw how to do this actually on Monday. We're going to just use an n-gram language model, right? So an n-gram language model can give you something that looks like probabilities of English sentences. And so I'm basically going to take those probabilities and multiply them by this translation model probability, and that will actually get us a much better model. So this idea of Bayes' theorem, which sort of underlies this, is actually very, very common. So there are a lot of other applications which you'll see this. So for instance, let's say in this case, essentially what Bayes' theorem tells me is I have some model which generates an English sentence, and then I go through some channel which generates this Chinese sentence. This turns out to apply in sort of all areas of machine learning, and I'll look at sort of sequence problems for a second. So you might have some model which generates English words, And then from that, generates images. So if you want to do OCR, you can sort of think of your problem this way. Or say that you have some training corpus of, I don't know, George W. Bush speeches. And so George W. Bush language looks something like this. And then, so you have something that generates this, and then that goes through some kind of process to generate this speech signal. So you can think of speech recognition as happening in exactly this way. I'm afraid this joke is going to expire pretty soon, or else it already has. Or perhaps you have some model of how genetic sequences arise and then are mutated to form new genetic sequences, and so you can do prediction problems on this. So anyway, the point is this is sort of digression just to tell you this is a nice way of modeling things. So anyway, language models. So we already saw a few days ago. You saw language models. So this is going to be a bigram language model. Basically, the probability of the first English word of the sentence is just going to be conditioned on some start symbol. And the next one, so it tends that in machine translation, punctuation like commas often tend to be treated as words, so that's something to point out there. And so we're just going to generate the whole English sentence this way, essentially just by multiplying all these probabilities together. So the probability of an English sentence is just going to be the product of all these bigram probabilities, or trigram probabilities, and so forth. All right, and so you already saw that, so I don't feel like I have to spend much time on this. So let's talk about what we do with these language models. So I already showed you this, this diagram. Okay, so this is the probability of Chinese sentence given an English sentence. So for a fixed Chinese sentence, you can actually plot that along the x-axis. You can plot the English sentences along the x-axis there, and then you can plot the probability along the y-axis. So now let's multiply in the English language model. So each English sentence, again along the y-axis, has some probability associated with it. And it looks something like this. And so when you multiply those things together, you get something that looks like this. So you're getting a completely new probability distribution over those English sentences given the Chinese sentence. And this is basically what we want to do. Essentially what we're doing, we're taking two classifiers here and we're sort of combining them to get a better classifier. You can sort of think of it that way. And so this is a nice way of thinking about this problem. But why should we stop there? So let's think about this for a second. These probabilities, as I've sort of laid them out here, are fixed. They're all between 0 and 1. But maybe I don't necessarily, we can also think of this. We can think of these probabilities as being raised to some exponent. And maybe I think that I actually believe this translation model more than I believe this language model. So maybe I want to do that. Maybe what I want to do is I want to sort of raise the power on that thing a little bit. And so what happens when I do that is I get a spikier probability distribution up here. And that doesn't affect this, but you'll notice, if you saw, it does actually affect this overall probability of the English sentence given the Chinese sentence. Or maybe I don't believe that translation model so much. In fact, it's much more likely to be the case. And so I want to take that power and I want to set it at something below 1. And so then I get sort of a much smoother distribution over those English sentences. And again, that's going to change the overall sort of predictor here that I'm using. Or perhaps if I don't believe it at all, I could set it to 0. In which case, this thing will turn out to be the same as this. So a different way of sort of accomplishing this is to take all these things and throw them into log space. Right? So I can just take that exponent. I can just essentially take a log of all these terms, and then I essentially get a predictor that the same thing, because of course log space is monotonic in the regular space. And so now what we get is a function that looks like this. Right? So here's the function that I'm actually going to use to assign probabilities to English sentences given the Chinese sentence. I basically just have some, basically it's just a linear formula, right? It's a linear interpolation between these two things. I'm missing a p there. And I have a z term that basically normalizes, ensures that this is a probability. And again, often I don't have to worry about this thing. When you're learning, you tend to have to worry about that thing. More generally, we could say that our formula looks something like this. Missing the lambda here. There should be a lambda I here. So lambda I. So basically, what we're going to do is we're going to take and have a linear interpolation between a bunch of functions on the combination of the Chinese and the English sentence. Right? And so I think you will have seen this a couple of days ago. So this is one way we can sort of arrive at this in this translation setting. Again, I'm just going to take the argmax. So I'm going to take the English sentence that maximizes that expression. So how do we actually find the English sentence that maximizes that expression? Basically, what I'm going to do, so now I have all these probabilities associated with segmenting this thing. I have probabilities associated with translating certain segments of it. I have language model probabilities. And I want to use these things to generate some possible set of candidate English sentences. Now, I can't enumerate all of the English sentences that might ever possibly be generated. So I just want to enumerate things that are quite likely. So what we'll do is we'll just enumerate things that have non-zero probability, say. So something which can be generated by some sequence of decisions in our probability model that are non-zero. How can I do this? Right? Well, in our phrase-based model, I can sort of reorder these things sort of arbitrarily, right? I can any sort of segment in here can be translated to something which can appear at the beginning of the sentence. So what I'm going to do, I know I need to incorporate a language model. And so what I want to do is I want to generate these possible English sentences left to right. So the way I'm going to think about this is I'm going to just pick out all possible English phrases that could appear at the beginning of an English translation of the sentence, and I'm going to generate them. The way I do that is I basically, I'm going to generate some large graph. So here are some decisions that could occur at the beginning of the sentence. I could have translated this large thing into some long phrase that ends with these two words. Or I could have taken this thing and I could have translated the word although. And it occurs at the start of the sentence. And I could have taken it and I could translate it as however. Okay, so all I need to remember while I'm navigating my way through this graph are the last two English words if I'm applying a trigram language model. And I'm going to multiply in each of these objects, each of these vertexes in this graph has some probability, which I basically just get by multiplying in the probability of the segmentation, the probability of its translation into whatever phrase I appended there, and any language model probability that's associated with that. Right? So now I could take this state and I could say, what can I do? I can't translate this word. This word is covered, and so I'm not going to deal with it anymore. But I could translate any of the rest of the words and append them onto that word although. And so there are actually many possible things that I could do here, so I'm just going to consider all of them. And so perhaps I pick these words and I translate them into some phrase that ends with wind shriek. Now, it turns out that there might be some other way that I could have reached the state through some other path through this graph. And so there might be multiple ways of reaching this sort of partial translation state. Basically, those things are going to end up at the same vertex, and I'm just going to take the best one. And so you'll see this sort of throughout this graph. So now, again, all I'm going to have to do is I'm going to have to pick up some words here, translate them, and append it to the end of that partial translation. And so maybe, again, we can translate out of order. So I might perhaps just pick up these words and sort of translate them. And again, the phrase that translates that ends with the sky. So we're just going to keep sort of wandering through this graph. And at each step, what we're going to do is we're going to cover up some of those Chinese words, and we're going to append the phrases to the end of the sentence until we're done. OK? And so now, at the done, I've now generated this humongous graph, which you've only seen just a tiny portion of. And at the end, I have these leaf nodes at the end of this graph. And I'm just going to pick the one that has the highest probability associated with it. And then I'm going to walk back along that path that generated. I'm just going to read off sort of the English words, essentially backwards, to get my English translation. And so it turns out that if I read off that path, I get a translation that looks like this. Right? So I want you to think about this large graph that we just navigated through. This is better than enumerating all possible English sentences, right? But it's still pretty bad. So here's an example of a vertex that you saw in that graph. So the vertex has some score associated with it, and its state is the vertex basically encodes that I've translated these Chinese words, and the last 2 English words I generated were those 2 English words. So let's think about all the possible states I could have in this graph that look like this. How many vertices are you going to come up with? Well, basically, you have to consider all possible coverings of all the Chinese words in that sentence. That's a large number of vertices, right? It's exponential in the sentence length. And so that's, and this is not even considering the fact that we have to maintain some English language model state, which is going to split those states even further. So that's a very, very large number of states. In general, it turns out that this is completely intractable. So we just simply can't solve this problem for sentences of longer than, length 6 or 7. So we can't do it exactly. So you can imagine running something like Dijkstra on it to try to get the exact answer out. And that's going to be at least linear in the number of vertices. So basically, what you have to do here is you have to resort to some kind of pruning. One way of doing that is sort of grouping these vertexes together under some function and basically sort of pruning out ones that are a long distance away from the highest scoring one and hope that you end up with a reasonably good translation. And the consequence of doing this kind of pruning is that you end up with some kind of search error. You don't actually end up with model optimum. And what you hope is what you end up with, because we're working with an ill-posed problem, is that you end up with something that's not too terrible at prediction. But essentially there is sort of no nice, clean way of solving this problem exactly. So it happens that in these phrase-based models, people often resort to hacks to make this a little bit easier. So one thing we could do, so the exponential complexity here is essentially due to the fact that we have to consider all possible coverings of the Chinese sentence. So in these phrase-based models, something we do is we often say we have some window. And here I'll call this window a length of 4. And I'll say only within this window can the covering be on or off. But outside the window, to the left, everything must be covered. And outside the window to the right, everything must be uncovered. And so essentially, this reduces the sort of coverage, that vector of coverages that we have to maintain to something that's exponential in this length d. And we have a linear term in the length of the sentence. So the number of vertices is now this. So, and this is actually how most of these models are implemented. This is a very, very hacky thing to do. And you'll notice one thing about this is that it essentially says that your translation has to be largely monotonic. It doesn't have to be completely monotonic, but essentially we sort of cut off the reordering past some distance. We only reorder within a small window. And now that seems kind of terrible, especially given the example that we just saw. We couldn't even translate our example sentence with this very small window length. On the other hand, sort of if you look at actual translations, they sometimes tend to be monotonic. Even if the languages tend to express things in very different word order, a lot of times the translators do actual great violence to the word orders of the sentence. And so this monotonic assumption it's kind of bad, but it sort of works okay. And so the reason we do this essentially is to deal with exponential complexity. What we'd really like is a model that doesn't have this sort of problem with this exponential complexity. So let's talk about how we might get rid of that exponential complexity problem. I'm going to show you a different model. So what I want to do is I want to have some model. I can translate words or I can translate phrases, but what I don't want to do is I don't want to just sort of permute them arbitrarily, because that's what ends up with this extremely nasty constant. So let's say we'll do this in sort of a phrase-based setup. So we'll take our sentence and we'll segment it into our phrases. We've already seen how to do this. And then we're going to say we have translations for each of those segments. So how are we going to reorder these in a way that does not do the following? So what we don't want to do is we don't want to have an exponential number of possible reorderings, and we don't want to restrict ourselves such that we can't move things long distances. So we want to find some balance between those two things. So I'm going to say the following. So here's how we're going to do our reordering. We're going to take 2 of these phrases. We're just going to pick 2 of them that are adjacent to each other, and we're going to say that those phrases can either they can either remain in the same order or they can be swapped. So in this case, I'm going to pick these two phrases, and I'm going to say they should remain in the same order. So I'm going to denote this x1, x2. Okay, and so at this point, these things cannot be reordered anymore with respect to each other, and in the output sentence, they will be right next to each other. Okay, so I've only covered a sort of a continuous span of that Chinese sentence, and there are only a quadratic number of continuous spans, and so there's only going to be a quadratic number of items that look like this. So now what I can do is I can either take two phrases that are next to each other and combine them either in the same order or swapped, or I can combine them with some adjacent hierarchical phrase like this, right? So I could take these two things and I could say, actually, I'm going to combine these two things which are adjacent to each other, but I'm going to swap their order. And so I denote this by saying this is x2 followed by x1. So all this x basically corresponds to the thing that it's this child. So here I want to, x2, x1 says I want to read off this thing here before I read off that thing. And then I'm going to keep doing this. So I could take this thing and return it in the same order. And then I'm finally going to output the period in the same order. So I've only actually reversed this small part of this sentence.
Can you just
Okay.
say that one, what happened with the comma would get
The comma.
It wouldn't move by the however.
Hmm?
The comma, the
Oh.
sky. I guess it would go.
Well, okay, so so this comma actually this is just the English translation of that Chinese word. And so the comma is going to appear before this English
It
segment.
just gets carried, gets pushed up, even when you swap.
Oh, yeah. So when I swap, everything that's under here will appear before everything that's under here. Does that make sense?
Yeah,
So-
what
so
would
every-
happen if
yeah.
we went to the beginning of the sentence? That would make sense, right?
Um,
You would just have a rule that says don't put a comma by the beginning of the sentence.
you
You know what I'm saying? If you got swapped all the way.
You could, so depending on how many phrases you have, you could imagine a series of swaps that would end up with that comma at the beginning of the sentence. That's possible. But the trick here is not that you can't necessarily move that thing a long distance, because you can move it a long distance. But the trick here is that these coverings are always going to be on continuous substrings of the Chinese sentence. And so I don't have to maintain some vector of, have I covered this word, have I not covered this word? The number of possible substrings is quadratic in the length of the sentence. And so this is essentially how we're dealing with the complexity problem here. Right, so the final thing I'm going to do is, now I've sort of made these inferences here. Now I'm actually just going to read off the English sentence in the right order. And so when I read off the English sentence, so now I'm reading off in the English language order, which basically says that I swapped those two things. And so what that does is, this is just this is kind of like an Alexander Calder mobile, right? You can think of this tree down here as basically, I can sort of swap any of its links in any order. And that's how I end up with the English language order. And so the nice thing about this is it allows you to move things quite long distances. So you can imagine some node up here at the very top which swaps the sentence, essentially swaps the beginning and end of the sentence. So you can move things a very, very long distance by doing this, but the inference is completely polynomial. In fact, it's cubic in the length of the sentence. So that's actually really nice. Now, I'm glossing over some details here. So for instance, we have to maintain language model state for these things, and now I have to maintain language model state on both sides. That turned out to be a non-trivial problem to deal with. I won't actually talk about how we do this, but this is a subject of a great deal of research at the moment, how to do this efficiently. But this object that we've used to sort of describe this, whereas the thing you saw earlier was basically, these phrase-based models are basically finite state. You're generating a lattice that encodes some states. Here we're actually dealing with something called a synchronous context-free grammar. So I think on Monday afternoon you had a grammar writing lab, and you probably wrote a grammar which looks something like the thing on the first side of this slash. This is a synchronous context-free grammar. And so what this synchronous context-free grammar says is that on the Chinese side, I generate things in order. On the English side, I generate things in the same order. Or on the Chinese side, I generate things in order. And on the English side, I reverse them. Right? And so what this does is this generates these sort of synchronous trees where the trees are isomorphic up to a reordering of the children. Right? So the children can be reordered, but in all other respects, the trees are isomorphic. And then at the leaves of these trees, I can translate English phrases or Chinese phrases. And so this is a way of moving these phrases around without sort of incurring exponential complexity. And so that's nice. Well, let's think about this for a second. So I can do this. Basically, I can actually do this inference in cubic time with very, very high constant factor. That turns out to be some of the problem, because if you just saw the phrase-based models, we can actually do them in linear time if we sort of apply a sort of egregious hack to them. And so it's not necessarily clear that it's better compared to the hacky form doing the phrase-based models, but this is a very nice and elegant way of doing this. So we can do this in polynomial time. The phrase-based models you can do in exponential time. So what does that tell you? Like, you can't get something for nothing, right? So if I can do this inference in polynomial time, that means I must be giving up something in order to be able to do this. So here's an example. So it turns out that by doing these binary swaps, there are certain types of alignments that you cannot represent just doing binary swaps. And so this is an example from real data. This is a paper that was published a couple years ago. This kind of alignment just simply cannot be produced by this series of binary swaps. Essentially, we have this sort of interleaved alignment where all the things that are next to each other on the source side are never next to each other on the target side. And basically, we have no way of representing this sort of using a series of swaps. And so this is essentially what you're giving up by being able to do these binary swaps. Now, it so happens that the binary model reordering actually covers something on the order of 95 to 99% of the actual observed data. It depends on which study you look at. So a lot of people have sort of looked at this problem. And it seems like, in general, doing this in binary doesn't hurt you too much. But it isn't sort of important and instructive to realize that you can't represent this with. Now, you can represent this with an arbitrary synchronous context-free grammar. So we just add more symbols to it, where basically what we say is that we take this thing and we permute it. So this synchronous context-free grammar can represent arbitrary permutations, and the cost of that is basically going to be exponential in the number of these terminals, these symbols here. Right? So in the limit, you can represent arbitrary reordering, and then you pay the price for that. But if you're willing to settle with something less and maybe not be able to model 100% of your data, you can do much better in polynomial time. Yes?
So what's the consequence of not being able to model this? Like, does this produce errors at training time, or can we detect these and throw them out?
Does it produce? Well, yes. I don't know if you can detect these and throw them out. Probably not. So generally, we just do inference with some model that looks like how we're. So we might sort of learn a model using a binary model, and then it just doesn't model this data correctly. It gets some errors. So all of these models that we deal with have all kinds of sort of inference errors, right? So we learn all kinds of bad things from them. And you just sort of hope when you sort of push all that stuff through the sausage machine that it just sort of comes out and looks like English. But yeah, so all of these models are broken, right? I mean, this is really the whole problem here. In machine translation, you really want to try to model the translation process, and you want a model that is tractable, hopefully, or for which you can come up with suitable approximations, and which you can learn. And so all of these things, there's a very strong tension between all these things. This is one trade-off that you might make. So I say, well, I want something that is theoretically tractable, but I'm willing to concede that I won't be able to model all my data. It's true that you can't model all the data with the other models that you saw as well. So this is not necessarily a bad approximation to make. Chris was saying something.
So one implication is that when you're translating from the French to English, there's no way to produce that translation. But
yeah.
That doesn't mean that you can't produce an acceptable translation, right? So if you just change that English to be, I believe we all find that unacceptable regardless of political party. Suddenly you don't have those crossings and you could model it under your SCFG.
Yeah.
But
So
you're right that in training it would be somewhat problematic and you might have to disregard more examples than you'd like to.
Yeah, so That's fair. And typically what you happen, we don't have any way of sort of disregarding the training examples, at least based on something like this. So we just learn some junk from it, basically. We'll probably learn some misalignments of some kind. Okay, so if you can sort of take these phrases and reorder them in this binary way, you can also think of the synchronous context-free grammars. We can actually sort of intermingle words, and we can actually. So I'm going to show you a slightly more advanced model. So this model, we're again going to translate phrases. So we're going to take some phrases in the middle of the sentence, and we're going to translate them. But now what we're going to do is we're going to take a larger phrase that contains these other phrases. And so we can take this larger phrase, and we can just translate that, and possibly reorder the subphrases. So here what we're going to do is we're actually going to take that larger phrase, and we're going to recursively reorder some subphrases in it. You can actually describe this again in this synchronous context-free grammar formalism. And so this model is going to combine a bunch of things. So it combines some restricted level reordering that's based on the synchronous context-free grammar. It combines phrases. These decisions, as you can see, because each of these arrows is a decision, basically we have some lexical notion of how these things move around. And so this model is called a hierarchical phrase-based translation. And so this is now a sort of very competitive model. A lot of people are using stuff like this. So to sort of wrap up these synchronous models, so synchronous context-free grammar. So now I've sort of gone through this and sort of mostly to sort of give you some of the intuitions behind. So we've got phrase translation probabilities or word translation probabilities, some hierarchical rewriting probabilities. And so one question is, have we sort of solved some of the problems that we have in these phrase-based models? Well, maybe. Again, the complexity is polynomial and sentence length. And that's nice. We just saw that by using a dirty hack on the phrase-based models, we can make them linear. And so it's not necessarily clear that's better, although it turns out you can actually apply the same dirty hack to these models. We would like to get out of the business of doing dirty hacks, but again, these things are intractable. And so often when you're building these systems, you do have to make these kind of trade-offs. So one last question is, can it help with fluency? So we'll think about this for a second. So if you took part in the competitive grammar writing lab, you probably wrote some grammar for English, right? Or some restricted set of English. And so often when you sort of look at translations, you imagine, when I have, the adjective before the noun, say, in English, that often translates into the noun before the adjective in Spanish, for instance. And so it's sort of natural to think of these sort of syntactic transformations. It's sort of happening at the level of these context-free grammar transformations in translation. And so you could imagine that rather than using these sort of arbitrary reorderings, that the synchronous context-free grammar that you use in translation on one side looks like an English grammar and on the other side looks like a Chinese grammar. It doesn't quite work that way, unfortunately. This is an area of a lot of research, and I won't actually walk through an example. I'll just show you the one that I found in the paper somewhere. And so here's this model where basically I have a lot of movement going on the English side, and then we have all these alignments. So you can see that this turns out it's starting to be a fairly hairy model. It's not hairy at all in the way of the sort of IBM models that I showed you earlier, but it's a fairly hairy model, and it's difficult to do inference, and it's difficult to do search. But it's a really cool model, and it sort of corresponds to our intuitions. Again, what we're trying to do is we're trying to model how a human translator might model. Well, in some sense, what we'd like to model is the data, but we also want to model something that is trackable and gives us good predictions. So this is an area where people are still doing a lot of work. There's some evidence that these systems are competitive. They're quite difficult and slow to run at the moment, but they're very interesting. So if you're interested in translation, I'd encourage you to look along these lines. So I do want to say one last thing. So we've run a system, we've generated some outputs. How do we know whether the output is correct, right? So this is a very big problem in machine translation. Some people think this is bigger than machine translation itself. So why do we want to actually evaluate these systems? So one is we built two systems, and we want to see which one is actually doing better. We want to, during system development, evaluate incremental changes, and we just want to sort of be able to assess new ideas sort of objectively. So we want to try two things out and see, whether they work better, or some improvement that I think of actually improves the system. So how can we do this? So one way is to look at the MT output. In fact, that is the best way. The best thing you should do is you should actually look at the output of your MT system. Now, if you're doing, and sometimes it turns out you look at it and it looks pretty good. And so this is basically, correct. The words are slightly different, but it means the right thing. Sometimes you look at the output of your MT system, and the words are sort of correct out of context, but they're not really quite right. So reading these sentences is kind of fun. But in general, if you get people together to sort of read MT output, a lot of times it tends to look something like this, and then you can imagine after doing this for a little while, you might want to claw your eyes out. But there are actually a lot of very clever ways that people in this room, for instance, have come up with to sort of make this a less repellent task for human. And so actually doing human evaluation of MT output and actually sort of comparing it subjectively is a very important thing to do. So that being said, there are many cases in which we simply have too much output to evaluate because we're doing incremental. So we're improving our system, say, every day. We retrain it. We come up with some new model. We retrain it, and so we have a new system every day of the week. We probably don't want to include time in that development cycle to simply read this output all the time. So we have some other way of doing this. So here's what we're going to do. So let's say this is our MT output from some sentence. So what we're going to do is we're going to So what we're going to do is we're going to translate. This is going to be a translation of a sentence for which we know the correct human translation. And so we already know the correct human translation of this sentence, right? We've already seen it. And so here's one dumb thing that we can do, because we want to do the dumbest possible thing, as always, to try to evaluate whether that sentence is good. What we're going to do is just compare the number of words that they have in common, right? And so you can see there's something like half the words are in common between the output sentence and the correct human translation, or a correct human translation. And so that's nice, but actually if you look at the sentence at the top, although it's kind of weird, it basically expresses the correct meaning of this sentence. And so perhaps saying it's only half correct is a little bit unfair to it. So again, what we could do is we could collect for the original Chinese sentence, we could collect some large number of translations. So maybe we get 4. And now what we can do is we can say, for every single word in the output sentence, does it appear in one of these references sentence? And so now we can see that we actually have a large number of matches. And so we actually cover a fair amount of that output sentence. In fact, we might want to count not only the number of words, perhaps pairs of words, so bigrams, or maybe even 3 words or 4 words. So if we do that, we can sort of look and see that in that output sentence, we actually cover, we have a reasonably high precision, at least at the unigram level, somewhat of the bigram, a little bit at trigram. And so we can basically develop a metric that takes some interpolation of these factors and returns you a score. Now we have to be careful, right? So we could have instead, our system could have output something like this. Right? It turns out that this trigram actually appears in one of the reference sentences, and so we don't want to be able to reward our system for doing something like this. That's bad. And so what we do is we add in some. So we've exactly matched all the unigrams, bigrams, and trigrams. So we're going to also include some term that basically punishes this for not being as long as the shortest or the average of any of these sentences. And so this is some way of sort of counterbalancing. But this is sort of a very hacky way of doing this. So there's a metric that's based on this very idea. It's called BLUE. And so if you read the MT literature for more than 5 minutes, you will see this. So it's sort of relevant to do. But I don't want you to get the impression this is the only way to evaluate systems. There are, as I said, there are a lot of different metrics for doing this. And so it's, this is maybe something interesting to look at if you're actually doing development of this. So one last thing I want to say about this. So BLUE is a function of the MT output, right? And if you remember, the MT output was simply just some function of some model which we developed by developing this complex series of models to score an English sentence given a Chinese sentence. So let's suppose we have some test sets in which we run. So we run our system to generate a large number of outputs, and we can score them automatically using BLUE. So if we think this blue or some other metric corresponds with human output, maybe what we could do is we could actually try to optimize that function. So this turns out to be a very, very nasty optimization function. But if you recall from the machine learning lecture, something we wanted to do is we wanted to have some loss function to which we optimize. And so if we believe that these automatic metrics correspond to human evaluation, we might try to optimize for them directly. So this is something like what the optimization problem looks like for that. And so as I said, actually doing learning on these models is incredibly difficult. And so that's why I left John to talk about it. So I don't have to describe how you actually optimize this horrifically nasty function. And so I think I will close with that. Thanks for listening to me blather on. I want to point out that there's actually a nice survey of a lot of the stuff in machine translation. It's located on that webpage, so feel free to go take a look if you want to look at this stuff in more detail.
Questions for Adam?
Just with you sort of stressed the dirty hacks thing, and well, we're not finding the actual solution to these problems. Do you have a sense of what percentage of the time finding the actual solution would have given you a measurably better evaluation?
I'd say in day-to-day development, a lot of times you don't think about this, but you can actually arrange these problems such that. So in general, finding the correct solution is intractable. The optimal solution is intractable, and so we use some approximation. But if you have a lot of time to wait, or you have a lot of CPU cycles, big machines, or you can do some other tricks. For instance, you can reformulate your problem as like an integer or linear program and throw it into some ILP solver. And you have a long enough time to wait, you can actually get the model optimal answer using some combination of these methods. And then you can compare the model score of the optimal answer with what you actually get out of your dirty heuristic method and see how much you're losing. Right? And so this is sort of commonly done. But again, because it's kind of difficult to evaluate these things, it's not always really clear. And it depends on the model, it depends on sort of the settings. But it's a useful thing to do.
So I think that I'm curious about your opinion about where you think the worst problems are. And let me list a few that feel like they're pretty bad. One is a serious mismatch between how we train the models and how we decode them. Right? So we have
That's a definite
alignment
problem.
schemes that we symmetrize, we do this, we do that. Then we have some other model that we use for decoding. They don't seem to have much to do with each other. So you might contrast that with speech, where you sort of have an HMM model that looks pretty similar between how you do the estimation and decoding. So that's one thing. Another is a mismatch between when you're doing this phrase-based translation, your language model, right? So you got these two pieces. You got your language model and your translation model. Your language model is going one word at a time. It's saying predict this word, predict that word. But your translation model is producing large chunks of words at the same time. Often with phrase probabilities of 1 that you then have some kind of lexical weighting or something to try to do about that. So there's this notion that if your language model is really being penalized appropriately for producing that next big chunk of words, that whole phrase, these probabilities might line up better. Let me leave it. Let me ask one more.
Okay.
So that's the second.
That might be a question that's best left offline. But
Sure.
I'd be happy to talk to you about
And then the third is, are we really doing the transfer at the right level? So, you can have these finite state models. There's a lot of interest in syntactic models. As you pointed out, there are problems where the syntactic transfer doesn't quite work as elegantly as it might when you first think about it. Are we really doing the transfer at the right place in the pyramid? Right? So where do you think the worst problems are?
Well, I think all of these things are pretty much, I mean, essentially, a lot of this sort of boils down to the problem that reordering sort of makes these things incredibly, incredibly nasty. So you have, no matter what model you come up with, if it deals with reordering in any intelligent way, it's going to be intractable, either while you're learning or while you're decoding, or both usually. But you want to trade that off with the fact that you want to try to sort of model you want to model the problem as best you can using a model that can still make accurate predictions, right? So you could imagine having, all of these models that I talked about, when you get the training data, you just have sentences. And so you basically have to infer some kind of latent structure over what is actually going on in there. And that could either be these word alignments, it could be phrase alignments, it could be syntax or semantics or whatever you think. You can sometimes you develop these latent variable models. You don't really know what they're modeling. It's unsupervised learning, so you just kind of throw it in there and hope for the best. And really, I think what that boils down to is whether the learning machinery we have is good enough to learn a more articulated latent variable model or not. And it seems to be inching in the right direction, but I think we probably still have several hundred more years to go. That's in the grand timeline of translation, that's not really that long. So I don't know. But yeah, I think all of these things are a problem. And the trick is really sort of finding the right way to sort of balance the tension between all of these problems.
How much does this problem benefit from like parse speech tagging or like parse trees or something like that?
Well, so a model that I showed you sort of the end is you can use English parse trees or Chinese parse trees or both to try to incorporate those into some model of translation. One of the problems there, of course, is that you're now modeling both English and or Chinese syntax and translation, and so these parsers are not necessarily 100% accurate, especially once you move sort of away from the Wall Street Journal or whatever they're trained on. And so by complexifying your model, you might hope to get a more accurate model of translation, but you also introduce new problems. And so, again, it's still a kind of trade-off. But that being said, people have in controlled settings, for some models have found some benefit from using these things. And I'd say that sort of the verdict is still out, but it's certainly it feels like intuitively that's where we want to go, and so I think that's why people keep hammering on it. So I don't actually know. Yes.
So this is going to be a linguist type of question.
Yes.
Since I'm a linguist. You said that about the binary swaps,
Mm-hmm.
and you had the example from French and English.
Yeah.
So suppose I think that happens more often if you're translating, say, between a European language and an American Indian language.
Yes. So one thing is that, so I sort of said at the beginning that we often claim these things are language independent, and then I kind of backed off. There are a lot of assumptions that go into these kinds of models. So for instance, the most basic assumption that went into every single model I talked about today was that there are word boundaries. Right? So Chinese doesn't have word boundaries. But another assumption was this sort of binary assumption, right? In the data that we often look at, it seems like that's a good assumption. But if you take another pair of languages which are understudied, it turns out that these assumptions tend to not hold. So,
Here's
yeah.
a question, since there are a lot of students here. I don't know if anyone's interested in American Indian languages, but if I gave you some like 500,000 words parallel text, could you tell me how often the binary swaps don't work?
So I could probably take this offline with you, but I'm aware of some studies where people have looked at this, and so no one's looked at the language pairs, so that would of course be an interesting thing to look at. So hopefully yes.
Questions for Adam? Okay, let's thank him again.